Welcome. In this video we'll go over CMOS power amplifiers, which we'll see are built a bit different than how bipolar power amplifiers would generally be built. And they generally use a push-pull approach in CMOS ones, and we'll see why that's the case. So let's get started. So as I mentioned, this video is going to look at CMOS Class A/B output stages and power amps. So we'll start off and we'll just assume that we'll use the basic BJT approach, but we'll replace our bipolar transistors with MOSFET transistors. And we'll see how that would be designed and what the disadvantages of it are. So in this case here, this would normally be an NPN emitter follower, and this would normally be a PNP emitter follower, but in this case they're both source followers and they're replaced with MOSFET transistors. Now to bias this, we need to generate a voltage. In this case we called it VBB in the bipolar case, and we'll call it VGG in this MOSFET case. And so we can use two diode connected transistors, Q1 and Q2, to generate VGG. We'll have a bias current, I bias, coming down that supplies the current through these two transistors. We'll have our input voltage applied at the bottom, same as we did with the bipolar case when we had two diodes creating our bias voltage. Now one thing we notice first is that because there'll be no current flowing through here, or effectively no current, because these are gates into MOSFET transistors, is that the current flowing down through here will still be just I bias. So we don't have to worry about the extra current. So ID1, the current flowing down through transistor Q1, equals the current flowing down through Q2, and that equals I bias. So it's independent of the amount of current that we happen to draw through QN or through QP. So we don't have to worry about that effect that we had to worry about in the bipolar case. That also means then that VGG will be constant, independent of how much current we're driving through QN and QP, our actual power transistors. I want to recall the formula for a transistor in the active region, or in saturated transistor in MOSFET world. ID is equal to mu n Cox over 2 times the width over length times V over drive squared. And we'll ignore the output impedance for this part of the analysis. We can rewrite that and say that the overdrive voltage is equal to the square root of 2ID divided by mu n Cox times the width over length. So let's look at IQ, the bias current. So the quiescent bias current, which would occur when the output voltage is equal to 0. So we have that the current through this transistor, Q1, is given by this formula, ID1, where we've just written V overdrive as VGS1 minus V threshold. We also have the current ID2, which is the current through this transistor here. And that's a similar equation. So now, using the equation that we have here, we can rewrite, we can now invert these two equations to find VGS1 and VGS2, and then we can see that VGG, the voltage here, is just going to be equal to VGS1 plus VSG2. So this voltage plus this voltage. So we have that VGG is the gate to source of the NMOS transistor plus the source to gate of the PMOS transistor. And so that means we can sum together our two threshold voltages and then our gate to source voltages, sorry, our overdrive voltages for each of them. And the overdrive voltages was given by this equation. And so this becomes the overdrive voltage for VGS1 is given by this part. The overdrive voltage for VGS2 is this combined with this. Now that is how we generate VGG. But of course VGG is also equal to the gate to source voltage of the NMOS transistor plus the source to gate voltage of the PMOS power transistors. So these two also have the same VGG as the sum. So we also have this equation here. So if we combine these two, and we're not going to do that here, but we can show that the quiescent current at the power transistors are going to be that bias current that we have at the top. So the quiescent current when V out equals 0, the quiescent current flowing down through here will be related to I bias and the relationship between these transistors. And the relationship between those transistors is given by this here. So it's combining the above equations. Now, if we assume that Q1 and Q2 are matched, so we've matched the mu n Cox, we've matched the mu n Cox with the length of this transistor with the mu n Cox with the length of this transistor. So they typically the mu p is different than the mu n, but we can always adjust the width over length of 2 and width over length of 1 so that the mu n Cox width over length of 1 equals mu p Cox width over length of 2. So we'll match the p and the n MOS together. We do the same thing for the power transistors, assuming that those are also matched. And if we do that, then the above equation simplifies to just be the quiescent current is the bias current and times the relationship between the width over length of the power transistor relative to the width over length of the bias transistor. Now, so that's how we can do our design for this, but we have a problem. The problem is that our output stage has a very small output signal range. So we can't go too close to the positive power supply, and we can't go too close to the negative power supply without it clipping. And we see that the V out is equal to VDD minus the bias voltage, so V bias, minus VGSN. In other words, this voltage here, if I call V bias over here as the voltage across our bias current here, so that might be an overdrive voltage or so, that the output voltage will be equal to VDD minus this voltage, so the voltage across I bias, and then minus the gate to source voltage of this transistor here. So that's what our output voltage is going to equal. So that's given by this equation that we have here. So the maximum output voltage we can get will be VDD minus the V overdrive of that bias voltage. So that might be a V overdrive for whatever that bias voltage be. It might be 100 millivolts or so, so not too much. But also minus the gate to source voltage, which is going to be the threshold of that PMOS power transistor, plus the overdrive voltage of that. So this is the key part here, is that the output voltage here, the closest it can get to VDD, will depend upon the overdrive voltage of this NMOS, this NMOS power transistor. And when we're driving a lot of current through that, that's going to be a very large overdrive voltage. So we see that this V overdrive N, so this term right here can be large, especially when we have our maximum current. It's going to be the largest when we have our maximum current going to the load. Now you might ask, well, why isn't that an issue in a bipolar case? Well, no, because the V overdrive of an NMOS transistor can be very large and typically much larger than the base emitter voltage of any bipolar transistors. Because we have an exponential relationship in bipolar transistors, typically the base emitter voltage is 0.7 volts. It might go up to 0.72 or something, or 0.73, but it doesn't get very large. Certainly doesn't go above 0.8 volts. Whereas the overdrive voltage of this NMOS transistor could easily become 300, 400, 500 millivolts in a power transistor. And when you add that together with the threshold voltage of another 300 millivolts, you've easily got 1 volt or 2 volts of loss that you have here. You can look at a similar relationship and you'll see that in the Vout minimum will depend upon the overdrive of the PMOS transistor. So you'll have a similar problem going to the negative power supply. So in general, what you'll find is that for CMOS power amps, they don't use this type of circuit. Instead, they go to a push-pull output stage, and that gets used instead, and this is what we'll talk about next. So next, we'd like to look at a CMOS power amplifier using a push-pull output stage. So this is a CMOS push-pull output stage. So you can see before we had an NMOS transistor, which was a source follower here. We replaced this with a PMOS transistor, which is now a common source amplifier. Similarly, we replaced the PMOS transistor down here in the previous output stage with an NMOS common source amplifier. And we've surrounded these with a gain, a feedback amplifier, gain mu here, and the similar feedback amplifier down here with a gain mu as well. And now the difference is that we're making it so that the output, the out, will try to follow the input because of feedback. So we can really think of this entire part as one amplifier stage here, and we have that Vout will equal Vi due to feedback, and there's a gain stage in the first part and another gain stage in the second part. And we have a similar part for the negative half coming down through here. So we now have that Vout equals Vi due to feedback. So as Vi, let's say that our impedance here is fairly low. So let's say that our L is 8 ohms. And we all of a sudden increase Vi. So Vi here goes up. We'd like this voltage here to also go up. So let's say it's supposed to go up to 10 volts. Then as this voltage is going up, this voltage will actually drop and it will pull more current through there. And this voltage will also drop and less current will flow down through here. So more current will flow down to here to rise up Vout until Vout will equal Vi. So we can see it's a push-pull because we're using two common source amplifiers. This one pushing current in and this one pulling current out. Now, if we didn't have any air amplifiers, because we already have a gain stage potentially from this point to this point, the output impedance may not be that high. So we can add this mu gain here, which reduces the output impedance. So if we don't have any air amplifiers, we might have a higher output resistance, and we'll see that that gets reduced by the gain that we have here. So we can reduce our output impedance of our amplifier. And as I mentioned, Vout is approximately equal to Vi due to feedback. So the challenge now is we need to design each air amplifier so that the bias current IQ will flow through the power transistors, which are IDP and IDN, when the output voltage equals the input voltage, which is equal to 0. So it turns out that we need to design these amplifiers separately. So we can't use a single amplifier. we actually use 2 amplifiers. So this is the circuit for the amplifier here. This would be that air amplifier. So this corresponds to this amplifier right here. And we can see that it has a differential PMOS pair coming in. And the output is down here through these NMOS transistors trying to match this QN transistor over here. In the other side, so for the upper air amplifier here, everything would be reversed here. So rather than having PMOS inputs, we would have NMOS inputs, and rather than having the loads being NMOS, they would be PMOS, and the bias would be reversed as well. So this would be a flipped amplifier for the top amplifier over here. So let's just start looking at the lower amplifier here. And so we're looking now at the IQ design for the lower air amplifier. So we'll assume that VI is equal to 0 here. And this is VI coming out over here. It also goes up to the upper amplifier. And we have the V out is equal to 0. And we want this current to be I sub Q. So we put a bias current of IB here. If we have this voltage equal to this voltage, then half the current will flow through here and half will flow through here. So we'll have IB over 2 on either side. Q3 and Q4 are going to be matched. So because this has the same gate to source voltage for 4 as for 3, and we have the same currents flowing down through them, so the drain to source voltage of 4 will equal the drain to source voltage of 3. So this QN will look like a current mirror based upon the diode, or the ratio of Q3 to QN. So what we have is that the current IQ is equal to the, as I mentioned, the ratio of the width over length of this large transistor here, our power transistor, relative to the width over length of this transistor, Q3, times IB over 2, because that's the current that's flowing down through Q3. If the lengths are matched, and typically we would like the lengths to be matched so we can have this matching fairly well, then it would just be the width of the N-channel transistor compared to the width of the transistor Q3 times IB over 2. And that's when the length of the N transistor, the large power transistor, equals the length of our bias transistor over here. And we typically would want the lengths to be matched so that we can have good matching between IQ and IB over 2. It's a similar design, as I mentioned, for QP, for the upper air design, but we now then use an NMOS differential pair input and PMOS current source loads. So everything is just flipped around. But we do the same type of design for it, and we also match it to IQ to be the same. Next, we'll look at the output resistance. So if we just look at the top half to start with, so we have the top half here, and we look at the small signal model, we can zero our input here, so VI would be zeroed, and we just want to know what is the output impedance here, looking back into this. So we have our load resistance on this side, but we're looking at just the output impedance. So to do that, and we'll assume that the this is the power transistor, this is our Q sub P, so this is this transistor right here. So it has a GM of GMP, and we'll have we'll say it has an output impedance of ROP. And we have our air amplifier, which has a gain of mu. So the gain of mu was the small signal gain from here to here. That's our gain mu. So now we have the output impedance. We can use feedback, and we can say that the output impedance, R out P, will equal the impedance we see when we open the loop times 1 plus the loop gain when that port is shorted, divided by 1 plus the loop gain when that port is open. So we've seen this in the feedback video in the notes. We have when we short that loop, the loop gain goes to 0. When the loop is open, the gain is just going to be the gain from here to here, which is mu, and then the gain from here to here, which is going to be minus GM times ROP. So the overall gain is going to be mu times GM ROP, and the negative sign cancels out because of the way we define the loop gain. ROP prime is the impedance that we see when we break our loop. And when the loop is broken, if we just break that loop at this location, we see an output impedance then of ROP. So the actual output impedance then here, capital ROP, is equal to our small signal output impedance of the transistor, ROP, divided by 1 plus mu n, not mu n, but mu, which is the gain of the amplifier, times GM times ROP. And if GM ROP is much greater than 1, we can approximate that as being just 1 over mu times GMP, where GM is the transconductance of that PMOS transistor. If you do a similar analysis, you'll find that the output impedance on the N side will be 1 over mu times the GM of the N channel transistor. So the overall output impedance is going to be the parallel combination of those two output impedances, which works out then to be just 1 divided by mu, where mu is the gain of the error amplifier, times the sum of GMP plus GMN. So the larger you can make those two transconductances, the smaller your output impedance is, and the larger you can make the error amplifier, the lower the output impedance is going to be. So next we'd like to look at the large signal V out over VI relationship. So we're going to assume for simplicity that mu n Cox width over length of n equals mu p Cox width over length of p. So in other words, we're going to assume for simplicity that we've matched the mu n Cox width over length of this transistor with the mu n Cox width over length of this transistor. So it has equal drive strength up and equal drive strength down. We can vary the width over lengths in order to make that happen, because the mobilities will probably not match. So we have matched devices for Qn and Qp. So when our input voltage is equal to 0, let's look at the DC bias to start with. So we want to look at our DC bias case, and then we'll start to look at the large signal behavior. So for the DC bias case, we set our input equal to 0, so Vi equals 0. Our output will also equal 0, so there's no current flowing down through here. We have our quiescent current that we've designed properly flowing down through the QP, and it equals the quiescent current flowing down through Qn. And so then we know that the voltage V source to gate of the PMOS transistor is given by this value. So that's the voltage from here to here. So now we know the voltage at the output of this error amplifier is given by this value here, VDD minus the source to gate voltage of the PMOS transistor. And we can do a similar thing for the N side. If this is the V gate to source of the NMOS transistor, then the voltage at the output of this error amplifier is minus VSS plus this voltage here. So we can write that the source to gate of the PMOS transistor is the overdrive voltage of the PMOS transistor plus the threshold, the magnitude of the threshold, in which case the overdrive voltage of the PMOS is the source to gate voltage minus the magnitude of the threshold. We can also say that the drain current, so the drain current flowing through the PMOS transistor, power transistor, we've said that's equal to IQ, and that will equal 1/2 K, so mu n Cox width over length divided by 2, remember K is mu P Cox width over length, times the overdrive voltage, which is V source to gate, minus the threshold voltage all squared. And that should equal the current through the NMOS transistor as well. because our output voltage is 0. In this case, we have no current flowing through the load resistance, so these two currents should match. So we see then that IQ is just equal to 1/2 times K times V overdrive of the PMOS transistor squared, which is also 1/2 K times V overdrive of the NMOS transistor squared. Now we need to discuss notation for a second. And we're using the notation that for a DC voltage or the bias voltage, we use a capital voltage, a capital letter with subscripts which are also capital. So V sub capital S sub G, S and G. For the small signal variations, we use a small v and the subscript is small s and small g. For the total voltage, it'll be the small letter with the subscript capital S sub g. So what we have is that the total is actually equal to just the bias voltage plus the small signal part on top of it. So V sub small letter with capital VSG, which is the total voltage, is the small signal plus the bias voltage. Now, we want to look at the case where VI is not equal to 0 and the output is also not equal to 0. So what we can say is that the voltage at the output of the error amplifier, so the output of the error amplifier will be the original voltage value plus the change and the small signal change. So the small signal change in this case is mu times V out minus VI. Remember, V out and VI might be slightly different because it's multiplied by the error itself. That becomes the small signal change that we see at this node here. So in other words, the new voltage that we see at this location will be the original VDD minus VSGP, which is the bias voltage, plus mu times V out minus VI, because that's the voltage V out minus VI, and this has a gain of mu. So that's the new voltage that we have at this location at the output of the error amplifier. We can have a similar relationship at the error output for the other error amplifier down here. So we can write that the actual voltage at VSG, so this actual voltage here, the total voltage, is equal to VDD minus this voltage here. So that voltage right here. So this is the actual voltage, is VDD, and this is the actual VSG. Sorry, that is the output of the error amplifier. Sorry. So what we see is the VDDs cancel out, and we get that the actual output on this node here, so the actual source to gate voltage on the PMOS transistor is the DC bias voltage minus mu times V out minus VI. So it's what we sort of expected. It's the small signal change on that. So we can then write VSG, which is the bias voltage, is equal to this term here. And then this term here is still shown over here. So now we can write the current through the transistor when V out is not equal to VI is 1/2 K times the actual source to gate voltage minus the threshold voltage. And we have that the actual voltage is given by this value, we see this part and this part will cancel out. So we end up with the actual current is given by this voltage here. So it's given by 1/2 K times the original overdrive voltage, but minus this small signal part to it and the whole thing squared. We can then factor out the V overdrive part here, which is dividing it through and bringing it out over into this part here. And so just rewriting that equation. And we recognize that this part here is our original bias current. So if we go back to our original part, we see that I sub q was given by this part right here. So what we have then is that the actual current through the PMOS transistor is the original bias current, which is given by this value here, but times this extra term here, all squared. So it's given by the original bias current times this 1 minus term. You can do a similar analysis and you'll find that the actual current for the NMOS transistor is the original bias current times 1 plus this. So the only difference between these two, so see that there's a minus sign here and a plus sign over here. So as one current is increasing, the other current is decreasing by a similar amount. Now if we assume that the overdrive voltage is defined to be the overdrive voltage of the P and that equals the overdrive voltage of the N. Again, just to make our life a little simpler, rather than to carry around a lot of extra terms. So we'll have a single overdrive voltage, we'll assume that they're both matched. Then we have that the output load current is the difference between the PMOS transistor and the NMOS. So in other words, this current I sub L is this current minus this current. So we can then subtract this one minus this one. What we see is that the squared, some of the squared terms will cancel out. So this, when we expand this term, there'll be a 1 plus a linear term and plus a squared term over here. The squared terms are going to cancel out. So we'll just end up with the load current is equal to minus 4 times IQ times mu times V out minus VI over V overdrive. And we also have that the load current is equal to V out divided by RL because it's the load resistance that we have over here. We'd like to now find the relationship between V out and VI, so we can substitute in this one into here, combine those two, and we'll end up that V out is equal to the input voltage divided by this term over here. Remember, this is large signal analysis that we've done, not small signal. We've assumed the actual equations for the MOSFET transistors and the square law equations that we have. So we see that that we're actually going to get a linear relationship between the output and the input, but it's going to have a reduction in the gain somewhat. Though if the V overdrive is changing, we should point this out, V overdrive can change as the currents are changing. So as the currents are changing, the V overdrive is changing, that will cause some distortion in this circuit, or in this equation. If we assume that V overdrive divided by this term is much less than 1, then we can say that VI divided by 1 plus X is approximately equal to just VI times 1 minus X. So we can make this simplification. The V out is just VI times 1 minus this term over here. So our gain error that we get, V out minus VI, is given by this term here. Since we have the GM is, and we're assuming that the GM of the NMOS equals the GM of the PMOS, we'll just define that to be GM. That's equal to 2 times the drain current divided by the overdrive voltage. We can also write down that the gain error then is equal to minus 1 over 2 mu, where mu is the gain of the air amplifier, times GM times RL. So as the currents are changing, we do have GM, which is changing. So mu would remain relatively constant, but GM is changing. And with GM changing, we will get gain error as currents are flowing through the NMOS and the PMOS transistors. So what we do see then is that having a large mu though here will reduce our gain error and as well as our output resistance. The challenge, however, is if we make it too large, is we end up with a high IQ can be highly variable because of mismatch and offsets between the two. So typical mu values that people will choose is 5 to 10 for this type of an amplifier. So finally, let's look at an example. We'll assume that we have a VDD equals minus VSS, which is 2.5 volts. So we have plus 2.5 volts here and minus 2.5 volts down here. We'll also assume that the threshold voltage of the N equals the negative threshold voltage of the PMOS, which is 0.5 volts. We'll assume that mu N Cox is equal to 2.5 times mu P Cox. So in other words, the mobility of the NMOS electrons is 2.5 times higher than the mobility of the holes. And that mu N Cox is equal to 250 microamps per volt squared. And so mu P Cox will be lower by 2.5. We'll assume that mu is equal to 10, so the gain of the air amplifier is 10. We want our quiescent current to be 1 milliamp. Our load is 100 ohms. We'd like to choose our overdrive voltage for the DC bias to be somewhere between 0.1 and 0.2 volts. So we can choose 0.1, choose 0.15, choose 0.2, but we'd like to have it limited within that range. And where should we choose it? So we'd like to find then the QN, QP sizes, and our quiescent operating points that we have. So what voltages we see throughout our circuit. So first off, we want to minimize our gain error and our output resistance. We want to maximize our GM because we saw before that we have a GM term right here, which affects the gain error. We've already decided what mu is, so we need to maximize our GM. GM is equal to 2IQ divided by V overdrive. IQ was given to us as 1 milliamp. So all we can really adjust is V overdrive. So if we want to maximize GM, we want to minimize V overdrive. We were given a range of the overdrive voltage, so we want to choose the smallest amount. We want to choose V overdrive equal to 0.1, so GM is maximized. So we have the GM is equal to 2 times 1 milliamp divided by 0.1, or it's 20 milliamps per volt in our DC bias conditions. That tells us that IQ is now, we know that's equal to 1/2 K times V overdrive squared. We now have V overdrive is equal to 0.1. We know that IQ is equal to 1 milliamp here. So we have this is 1 milliamp. Mu N Cox was given to us with the length of N we're trying to find, and 0.1 is the overdrive voltage. So we're trying to find width over length of N. We know everything else in this equation, so we can solve for width over length of N, and that's equal to 800 in this case. You can do a similar analysis for the width over length of the PMOS, and it'll end up being 2.5 times higher because of this term here. So 2.5 times 800 works out to be 2,000. And that's because the mu P is 2.5 times less than mu N. The output resistance then is 1 over mu, which is the gain. Remember, it's the gain of the air amplifier times GM plus GMP plus GMN. These are both 20 milliamps per volt. So the overall output impedance is 2.5 ohms. So it's fairly small. So finally, if we look at the actual voltages then, we have that VSG will be the overdrive voltage, which we said was 0.1, plus our threshold of the PMOS transistor, which is 0.5. So we have a VSG is equal to 0.6. So if this is 2.5 volts, this is 0.6. So we have voltage at the PMOS transistor will be 1.9 volts. If this is negative 0.25 volts, this will also be 0.6. So this will be negative 1.9 volts. And that will be our bias condition when the input and output are both equal to 0. That ends the example, and thanks for watching.